right? That table, that dreaded table that we went over in class. I'm not going to give you the table. You don't need to memorize the table, right? We know the equation, delta G equals delta H minus T delta S. So we should be able to think about what conditions do I have? Is that favorable? Is that not favorable, right? So if I have an exothermic reaction, that's good because that's releasing heat to the universe. It's heating the universe. That increases entropy for the universe. If that exothermic reaction also has a positive change in entropy, that is also favorable for us. So both of those things are favorable. Releasing heat, increasing the temperature of the universe, increasing the entropy of the universe. Positive delta S is also favorable for the reaction, increasing entropy. That reaction, if I have a negative delta H and I'm subtracting a number from that, it's just going to get more negative. So I'll always, always, always have a negative delta G. This is always spontaneous, regardless of temperature. So if I flip that, right, if I flip those conditions, delta G equals delta H minus T delta S, if that reaction, if I flip that reaction that's spontaneous, always spontaneous, if I flip that reaction, it goes from being exothermic to endothermic, and it goes from having a positive entropy to a negative entropy. An endothermic reaction absorbs energy from the universe, so that cools the universe. That's not favorable. That hurts us. That goes against us. And if I have a decrease in entropy, that is also not favorable. So now I've got two things that are hurting our chances of being a spontaneous reaction. Endothermic positive delta H, and I'm going to always be subtracting a negative number. So subtracting a negative, you're really adding that across. We will always have a positive delta G under these conditions. This will always be non-spontaneous. Doesn't matter the temperature, non-spontaneous. If you know one, you know the other one because you're just flipping the signs of both. Where it gets a little bit tricky is where we have something that's exothermic, but a decrease in entropy, or something that's endothermic, but an increase in entropy. So we'll do that one first, right? Delta G equals delta H minus T delta S. So we're going to do an endothermic reaction that has a positive change in entropy. So an example of that is, right, ice turning into water. It's a process. It's endothermic. It absorbs energy, but with respect to entropy, it's favorable because we go from a solid to a liquid. So let's think about that, right? Ice turning into water, that's endothermic. At low temperatures, ice stays ice, right? That is not spontaneous. At low temperatures, ice stays ice. As temperature increases, however, this process becomes spontaneous. And so I have an endothermic process. That endothermic process results in an increase in entropy. So what that tells me is that as temperature increases, eventually I'm going to subtract a large enough number and it's going to cancel out my delta H, and I will have a negative delta G, and it will become spontaneous, right? So non-spontaneous at low temp, and that'll be spontaneous at higher temp. If it helps, I would definitely link it to an example, like ice melting. That's endothermic. Here in Syracuse, we're very familiar with ice forming, right? That happens. ice stays ice at low temperatures. As we increase temperature, right, it will melt spontaneously. So the other example, we're just going to switch the signs. So delta G equals, now we've got an exothermic reaction, and that exothermic reaction results in a decrease in entropy. So now the opposite would be true, right? Now the opposite is true because my exothermic reaction, all right, I've got an exothermic reaction, but I'm going to be subtracting a negative number, which is adding this across. So when temperature is low, negative delta H will win, and I'll have a negative delta G, and this will be spontaneous at low temperatures. However, as temperature increases and I subtract this negative number across, eventually I'm going to be subtracting a negative number that is larger than my delta H. It cancels out my delta H, and I'll have a positive delta G. All right, so let me just write out that example here. Now the example would be water, right? Liquid goes to ice. So again, just to work through that another time, this process is exothermic. It releases heat. And we know it's spontaneous at low temperature. It has a decrease in entropy because we're going from a liquid to a solid. We know water spontaneously turns into ice at low temperature. And as I increase temperature, right, eventually at a high enough temperature, water stays water, right? It no longer turns to ice. So we are spontaneous at low temp, at higher temp. The other way to think about it too, that I mentioned in class or in office hours today, is the negative entropy is hurting us because that's a decrease in entropy, right? Second law of thermodynamics, we want entropy increasing for the universe for a spontaneous process. So the larger this temperature becomes, the more this decrease in entropy is affecting us. And so it makes sense that eventually a temperature gets large enough that this is actually going to get to the point where it stops our process, or it stops our reaction from happening, and switches from being spontaneous to non-spontaneous. So yeah, you don't need to memorize the table, right? It's just a matter of, we know the equation and just putting together, what's the sign of delta H, what's the sign of delta S, and then what would happen. I could go with 1 Kelvin, I could go with 1,000,000 Kelvin. So as I change the temperature, what happens, what might happen to that sign of delta G, to figure out, is this reaction spontaneous or not? And I'd also try to just pair it with, an example as well, right? Endothermic, that's ice melting. Well, we know low temperatures, ice stays ice, but as temperature increases, that switches and it becomes water, right?